on this computer. Okay, now good morning everyone. So we have discussed already about your performance in the long test, and I've given you a makeup long test one in MATLAB exercise so that you can recover from your scores, and then that will be the end of planar control, so of planar robot control. So what we did was we have basically completed all the possible controls in terms of planar motion. That means that we have make forward kinematics and inverse kinematics in planar robots. And also we have introduced transformation matrices. Okay, that a transformation matrix is composed of a rotation part and a position part. Okay, so now this time we are going to introduce Denavit-Hartenberg convention that is used to derive those transformation matrices. Okay, so the problem here is that the basic problem of Denavit-Hartenberg convention is that given any robot, we should be able to compute the transformation matrix from each of the joint, so that we will be able to see the end effector position and orientation with respect to the base. That means the series of transformation matrices, as we know, then you will have the resulting transformation matrix of position and orientation of the end effector with respect to the base. Okay, that's the idea. So now, what is this Denavit-Hartenberg convention? Okay, so we have the homogeneous transformation matrix, this one that I have mentioned already. Then this part, this is the rotation, and this part is the position. And then the whole matrix, the entire matrix, is the position and orientation of frame 2 with respect to frame 1. We call it transformation matrix. In this class, we call it letter A, big A. So now, in this, physically, this is what happens. So this is frame 2, and this is frame 1. Okay, let's just for the sake of discussion, we assume frame 1 is stationary. Okay.
So can you share the screen?
Oh, I'm sharing. Sorry.
Yes, sir.
A lot of people have been. Oh, sorry. Okay, let me start. There. So let me go back. Do you see this now? You see the screen?
Yes, sir.
Okay. Okay, so this is lecture 4 for Denavit-Hartenberg convention. Okay, so in this case, we have in the last lecture, we already know about the transformation matrix, which is in our class symbol that we use, it is A. So in this case, this is frame 2, transformation matrix of frame 2 with respect to frame 1, where it is consists of two main components. One is the rotation matrix that we know already, rotation of frame 2 with respect to frame 1, and the position vector P, which is the position of frame 2 with respect to frame 1. So physically, you can see that this is frame 2, which is the red frame, and frame 1, which is the black frame. So for the sake of discussion, again, we say that the black frame 1 is stationary. And then the red frame 2 moves with respect to frame 1 in terms of position. So position, when talking about the position, it is the position of the origin of frame 2. This point, the origin is a point. This point of frame to origin of frame 2, where is this located with respect to frame 1? And we connect those 2 points, the origin of frame 2 and the origin of frame 1, with a position vector 1, P2. Okay, that's a vector. Now, how is the rotation matrix oriented? I mean, how is frame 2 oriented with respect to frame 1? Okay, so you must imagine, you must be familiar that position can be investigated separately with respect to orientation. Why is that? Because those two things, position, and orientation are independent of each other. You can investigate them separately. Okay, one doesn't influence the other. Okay, so that means that in this case here, when you're just investigating frame 2, with the orientation of frame 2 with respect to frame 1, we can put this frame here. I don't think, okay. We can put this frame, let me annotate. For example, this frame 2. Okay, this is frame 2. And then we do frame 1. We can have frame 1 here. Okay, this is frame 1. In this case, you still have rotation of frame 2 with respect to frame 1. It's the same. It's the same as this. Although in this case here, this is rotating. The change, there is a rotation as well as a position. But as I said, you can separately investigate orientation and position. So if you're only considering orientation, you can do this. Okay, you can put the frame without moving. You can just rotate one frame with respect to the other. It's the same as this is the same as this case. Okay, and the same thing also, you can say that frame 1, that is just a point. Okay, the origin of frame 1 with respect to the origin of frame 2, that is just a point. Okay, there. Then this is the same thing, 2 with respect to 1. Okay, because when you're just using position, you are considering only the origin. We are considering only the points. Okay, without even considering. Okay, of course, we are considering the axis of frame 1 like this, because there is okay, that is necessary in terms of what are the components of 1p2 with respect to x, 1p2 with respect to y, and 1p2 with respect to z, because that's how we plot them in the three-dimensional space. But from frame 2, the frames of frame 2 is not necessary because we're just considering the origin. Any questions with that? Okay, so always remember that we can investigate them separately, and then it will be the same. So that means that, for example, even here, okay, so if you want to do 1A2, it can be separated also. That means that you can put it in two actions. Rotation only, 0, then 0 here, which is the vector, multiplied by the position only. So this is identity, 3 by 3 identity, and then 2p1, 0, 1. Okay? This is equivalent to this. Even mathematically, if you compute, if you multiply this, it will return that. Okay? But in this case, we separated it. There's a rotation only, and there's a translation only. Translation meaning position movement only. Okay? The identity, if the rotation is an identity, it means there's no change in rotation. It's no change in orientation. Any questions? No questions? Okay, let's move. Okay, now we mentioned this before, and in fact, in our long test 2, we have computed them. That means that we can have a chain of several frames. Okay, this frame 1, frame 0 to frame 1 to frame 2 to frame 3 to frame I-1 to frame I up to frame N. where we say frame n is normally the end effector frame, means the number of, normally n represents the number of joints. Yeah, so joint here is the base, and then joint 1, joint 2, and so on until the nth joint, which is normally at the hand or the end effector of the robot. This is the base, and that's the end effector. So to know the transformation matrix, the total transformation from the base, which is frame 0, to the end, which is the end effector or the nth joint, it will be equal to 0 an, which we know this already. And so we can have post multiplications, okay, 0 a1, 1 a2, 2 a3, until, what is this? We can have, okay, if you want to do the, then you'll have, here we will insert dot I minus 1a, and then you have ai, okay, dot until this one, n minus 2 a to n minus 1, okay, and then n minus 1 a n. Okay, okay, I'm just emphasizing that you can have your I frame. I frame can be any frame within the range of 0 and n. Okay, so you can put I here somewhere, or you can even put I as the 1. Yeah, but then it's between 0 and n. Okay, so you make those series of transformations to find the transformation matrix of the base frame with respect to the end effector frame. This one we know. Okay, next. Now we go to how do we assign frames between joints. Okay, this is now, we are following what we call a Denavit-Hartenberg convention. Why do we need this convention? What do you think? Why do we need a convention to define the transformation between two joints? Why? Anyone? Mudiakotla, si Cabo? Why do we need a convention to represent the relationship between two joints? Why can we not just use the rotation? We know rotation matrix and the position matrix. Why cannot just we use that? Why we need to have a convention? Chicago? Why are you hiding? Udaya Kotla. Hey. Are you there? You don't want to answer.
Can I attempt to answer, sir?
Huh?
Can I attempt?
Okay. Why? You want to help Mr. Cabo?
Yes, sir. Yes, sir. Maybe because both of the links and the joint itself could move while in the trajectory. While they're still moving, the position of the joint itself can move.
The position of the joints itself, yes, it will move. But why? Why do we need to say that this should be how you're going to define the relationship? Well, we know rotation and position already.
So I think it's because this is the most, two joints are the most basic form you will have. If you have more joints, then you'll be building on one representation of those two
Yes,
joints.
that's right. That's right. That's correct. Because two joints are the basic relationship. Yeah. And then you have more joints, it will be built on those two joints. And then you just do again. I mean, you'll just iterate into as many joints as you have, then you'll have that overall relationship. That's correct. But the question is, why do you need a convention?
A convention, could it just make things simpler instead of going through the whole?
Come on, tell me, why do we need a convention?
Isn't the convention just there to make things easier and simpler? To have a simpler method to do things instead of having to rotate it and then find the position separate. I don't know.
Yes, yeah, of course, convention make things, easy to follow and everybody knows about it. Yes, but there's a very basic fundamental element here. Okay, anyone besides Mr. Inque?
I think it will be nice to have.
Ito Meleng, make your voice
standard.
loud.
I said, I'm thinking it will be a good thing to have a common standard that all the links and the computations will be made. That will make it easier to maybe have that convention in which this is the procedure in which the position and the orientation of the robot is going to be done.
Okay. Yeah, again, there's a, I'm looking for something. Mr. Inwako?
Yes, sir. Yeah, like you said, right, it will be better to have a common standard of doing things. And yeah, that's it.
Okay, yeah, it's true that once you have that, that is true. You know what you're saying, that there has to be a convention, yeah. Because once you have this kind of relationship, the transformation matrix, and you follow the DH convention, then we are sure that this is how things are. But how is that? What are we sure about?
So you didn't share the screen.
Oh, I didn't share the screen. Okay, sorry. Thank you. I'm not as nimble as I was when I was younger, I guess, Okay, now, but what is it? What it is that we are sure about? Any guess? Horada? I'm calling on the ladies because, I don't know why both of you are having difficulty in the long test one, but yes.
Can you repeat the question?
Why? What is the use of this convention? Why do we need to have this convention? And what does it do to us? What are we sure about? They're saying that, yeah, convention is necessary because everybody will think that we're following the same thing. Yes, but what does it do? What is it that we are sure about?
Well, it gives us the steps to follow when computing the rotation and the position at the same time.
Yeah. Okay, so maybe let me just answer it. Okay, the reason why we need the Denavit-Hartenberg convention gives us a way of really knowing how the frames are oriented or how the frames are placed on the robot links. Okay, And then once we follow that convention, voila, we know exactly that this is the joints, and we know the frames are exactly placed like that. Once they're placed like that, oh, okay, we know. We can compute already the transformation matrix. Okay? There are parameters that will define the transformation of one frame with respect to the other. And the frames are oriented in such a way with just 4 transformation. From this frame, we transform 2 translations and 2 rotations, and then we can go to this other frame. So with that 2 translations, with the convention of following how the frame should be oriented, and then with the 4 basic transformations of position and orientation, 2 transformations of position and 2 transformations of orientation, we will know exactly the relationship between these 2 frames. That's all. So it's just true that we need a convention to agree that, you know, once we follow that, we know exactly the relationship between the 2 frames. But the point is that this, if we follow this Denavit-Hartenberg convention, we know exactly how the frames are oriented because of that convention, and we know exactly how the frames transformation is done from one frame with respect to the other. Okay, so now this is the way on how we assign frames. So this is a convention on how to assign frames for any joint. So this is joint 1 and joint I-1, or you can put joint 1 or joint 2 or joint 0 and joint 1, and this is joint 2. Yeah, this is how we define the frame, how we orient the frames of for each joint. And then this is how we are going to define 4 parameters. 4 parameters that will define the basic transformation process. Okay, so the basic rotation or basic translation that will give way to how we transform from one frame to another. You need 1 translation, 2 basic translations, and 2 basic rotation transformations. Okay, so let's go back and have the details of that convention. So now, so the first important detail is that you don't need to memorize this, because whenever we have examination, you know, I will give it to you. Yeah, nobody, even me, I don't memorize it. Okay, but this I just know by the rule of thumb what is the convention, but I don't memorize it. Anyway, I will give you this convention. So now for joint I, okay, joint I with respect to joint I rotates about Zi-1. Okay, so what does it mean? It means that the movement, okay, right now we are only considering rotational joints. Okay, the translational joints can come very easily, but for now let's just consider joints that rotate. Okay, excuse me. So now one joint rotates with respect to the Z-axis. That's important. Okay, so that means that if this is the joint, okay, I'll change the color. If that is the joint, if that joint rotates there, that joint rotates here, and that joint rotates here, okay, this must be a Z-axis. This must be a Z-axis. This must be also a Z-axis. Okay, what is the index? We don't know. We will assign it later, but for sure these are Z-axis. Okay. Okay, let's start with that one. So you have joint I. Okay, we say joint I rotates about Zi-1. So if this is joint I, so this is Zi-1. Okay, because joint I rotates about this. Okay, so it's like this one. You have a link, and then it rotates about this axis, this link. Okay. Okay. This is the axis of rotation. So it will move like that, it will rotate, and then it will bring the link with it. Okay. So now, so this is ZI, and this ZI is the rotation axis of ZI plus 1. Okay. So that's the first convention. Okay, next, the XI is the common normal and intersecting both ZI and ZI minus 1. Okay, so when we assign this, we are assuming that the frame I minus 1 is already defined. Okay, so here we are saying that this frame I minus 1 is already defined. That means if that is Z, okay, it has Xi minus 1 here, and it has Yi minus 1 here. Okay, we are not sure how it is oriented. Okay, but okay, we are assuming that this is already defined. Now we need to define where is Xi and Zi and Yi. That's the question of the Denavit-Hartenberg representation. Okay, we define the frame I minus 1 is already defined. Now we need to define where is, how is frame I being oriented, and where is its origin. Okay, it is frame I that we are trying to build when we're trying to do this convention. Okay, now, okay, let's just for now, let's concentrate. Okay, just remember that frame I minus 1 is defined. Now, axis I is the common normal and intersecting both ZI and ZI minus 1. Okay, where is ZI minus 1? This is the one. Yeah, and ZI, this is the one. They are both intersecting both. Yeah, intersecting both. So a line will intersect. Okay, this line will intersect that line. Okay, this is ZI minus 1. It intersects there. I mean, this ZI intersects here. This must be XI because we are looking at where XI is. And then it also intersects ZI minus 1. Okay, this is also XI. It will intersect both axes. Okay, that's one requirement, intersects both ZI and ZI minus 1. The second requirement is that it is a common normal. Common normal, that means that it is perpendicular to both axes, ZI and ZI minus 1. Okay, that's the constraint. Okay, it is a requirement. And so we need to find a way for them to be both perpendicular to both two axes and also intersecting. Okay, so as you can see, this is the one. This axis is that. So if we find this axis, we can give this axis also that is perpendicular and that's perpendicular. Can you do that? Can you imagine that? How is it? Well, if I have two pens, it's really difficult to see now because I will unshare my screen and make myself bigger. I will stop sharing. Okay. Then I will make myself bigger. There. I should be the biggest person here. No, how come it's not me? Speaker view. I'm the speaker. And it's not showing. How come it's Miss Urata that is showing? How do I do this? and it doesn't go away. Is it because I pin your video? No, maybe let me pin video. Okay, there that's me. Okay, now, so there are two axes, yeah, that two axes. Maybe this is zi minus 1 and this is zi, yeah, and so they can be oriented in many different ways. Okay, orient like this, orient like that, orient like that. So now this is our xi that will intersect both axes. Okay, but they will intersect in such a way that it will be perpendicular to this and also perpendicular to. So for example, let's say both are like that. Yeah, both are both axes are what is this now? Are standing like that. Yeah, and so if we have an axis here, a horizontal axis, for sure in this case this is satisfied. That requirement that xi intersects both axes and are perpendicular to both zi and zi minus 1. This is satisfied. You understand? Yeah. So what are the other things that will satisfy that condition? Well, if we rotate this axis like that, they're still perpendicular, right? They're still both perpendicular to the axis, yeah? But if they're oriented like this, they are not anymore perpendicular. So we need to find a way how to position your axis so that it's perpendicular to both. Yeah? So if physically, you know, there could be a constraint because physically, if physically the axes are like this, then it has to find like that. It has to find a different orientation so that it can be perpendicular to both. You understand? You need to position your axis so that it can be perpendicular to both. For example, like this. There's a physical constraint that, for example, like this. If the axes are like this, yeah, and then it's so difficult to find how are we going to make it perpendicular to both. So maybe here, and then maybe like that, and then we have to reposition so that you can be perpendicular to both and intersecting like this. Okay, so that's the physical constraint. Okay, so anyway, that is the convention that that's the convention that should be followed in this. This is the physical constraint that should be followed in this Denavit-Hartenberg convention. So, where are we? Okay, let's continue. So that's the second requirement, and the third requirement that the yi completes. That's all. The yi completes the right-hand coordinate system. That means in this case, yi looking at where the yi is not very critical. So what once we define all the z-axis, let's just do again. Sorry. Okay, we only do z-axis, zi is there. And then we define zi minus 1 is here. Okay, so now we say that our xi is here, so that this is perpendicular to here. Okay, this is xi, perpendicular, that's perpendicular to zi, and also perpendicular to, perpendicular to zi minus 1, also perpendicular to zi. And this is your xi. Okay. Any questions? Okay. So once we define zi and xi, that's okay. We can, well, yi will be somewhere here. Okay, by that convention, but this is not necessary. So we don't need to show yi because it will just occupy space and it's not critical. Okay. Oh, there's something wrong. It's a big mistake. Okay, it's a huge mistake. I didn't. Okay. So it's a huge mistake that I did. This is joint I. This is joint I, and it rotates about a ZI. Okay, let me go back. I'm sorry. Well, we all commit mistakes, but I'm sorry. The mistake is that, okay, let's go back. Okay, it's still correct that all this rotates about the z-axis. It's all this rotates about the z-axis. My mistake is that this is joint I and rotates about zi minus 1. So this should be zi minus 1, sorry. That's my mistake. That's my mistake, that this should be zi minus 1. So if this is joint I minus 1, so it will rotate about zi minus 2.
So please repeat that again.
Yeah. Okay, let me repeat it. Okay. The way I presented at the start, we say that our z-axis, okay, the rotation, all the joints rotate about the z-axis. Okay, that is clear. Yeah. So this joint must be the z-axis. A z-axis, this joint rotates about another z-axis, and this joint also rotates about another z-axis. Okay. So that remains the same. My mistake was that I will call this joint zi minus 1. It's not correct because this is joint I, and joint I rotates about that axis. Okay, because before I say joint I, this is joint I, it rotates about here. No, joint I rotates about this axis. Okay, so yeah, it's like this. There's no previously I say that this joint rotates like that. The joint here rotates here, but no, it is the joint here. The joint here, it doesn't matter the length. The joint here rotates about that. Okay, that joint rotates about this axis. Okay, so that's that was my mistake. That I attached a link before so that this joint rotates about that. No, it's this joint rotates about this. Okay, so now this will be zi minus 1. Everything else will remain the same. It is just at the index it's wrong. Okay, so this is a joint I rotates about zi minus 1. So if that is the case, that joint rotates. Okay, let me just make it a different color. So zi minus 1, and then the rotation. Okay, this one rotates about there. Okay, so this axis is zi minus 1. So if this axis then, if this is joint I minus 1, so that axis will be rotating about zi minus 2. Because following this convention, it rotates about whatever index you have I, it will index minus 1. So if this is the case of joint I plus 1, so the index is z, it rotates about that axis, which is z of whatever I this is minus 1. So this is I plus 1 minus 1, so that's zi. Okay, it is just the index. Okay, anyway, so okay, so here this is zi minus 1. So now let's concentrate on this part because we are looking at zi minus 1 against zi. So that's why here this is so in this case here I was I was defining the relationship of this axis with this axis. So that's why I was able to define this. Okay, but it should be, because I called it Zi minus 1 and Zi. But the Zi minus 1 is this and the Zi is here. So again, let's just repeat the same process. Okay, so I will discuss this again later, but let me finish this Zi minus 1 and Zi relationship. So now we say that this is joint I and it rotates about Zi minus 1. This is now okay. And this joint I plus 1 rotates about Zi. This is now okay. So now Xi is a common normal and intersecting both Zi and Zi minus 1, because this is Zi and this is Zi minus 1. So we define an Xi. So again, another axis. So in this case, we define here Xi. Okay, Xi is that yellow axis. Can you see it? Maybe I use B. This is Xi. Okay, of course, this still remains Xi because it's the same axis. And this Xi is, again, we say common intersecting both Zi and Zi minus 1. So that's intersecting. So it intersects, right? This one intersects and this one intersects. Okay, that's already, one is already satisfied. One condition is already satisfied. The other condition is that they're common normal. The same thing, we have discussed it already. This is normal to that. X is normal to Z. Xi is normal to Zi minus 1 and also normal to Zi. Okay. And then because this is X by right hand rule, this is X and this is Z, so Yi will be there. Okay, now if you say Yi is there, so now you have defined the frame I using these three conventions. Okay, again, we define the frame, where the axis of the frames are and where is its origin. Okay, the origin is here because this is where they are intersecting. Okay, later we will see that it will be intersecting on the origin. These point of intersections will be the origin. Okay, wherever you place it, that is now your origin. Okay, well, sir, can you place the other intersection? Because we can intersect also here. We can also intersect here. Okay, this is parallel to Xi. Okay, sorry. We can also intersect here. Yeah, that is also satisfied. Yeah, it's intersecting and also perpendicular. Yeah, also perpendicular. Is that okay? What do you think? Can we move the axis here? And now your origin is here and your origin is here. Is that okay?
Yes.
Romokate, what are you saying? Come on, say it. Your fingers are saying something. Yes.
Yes, I think you can take it as the origin.
What?
So, yes, I'm agreeing with you.
Agreeing to me? I'm asking. I'm not saying a statement. I mean, I am asking.
Yes, I think you can take it as the origin point.
You can change it.
You can take it. You can also consider it.
You can also take this one.
I think so. Because it's also perpendicular.
Yes. That's right. Yes. You can also use it, you know. You can slide it anywhere. It's fine. But now, when you define the parameters later, it will change. I mean, the distances, you have to consider these distances. But once you define it, you attach it like that, then use that. If you choose this, use that. If you choose this, use it. Okay? As your convention. And then later, when you define the parameters, it will be used to whichever kind of whichever frame you assign, that will be based on that. You assign all those parameters based on the frame that you have chosen. But this one is okay. This is okay. You can use this, but this one also is okay. You can also use it. But when you define the parameters, some parameters will change because the position, the location of the origin are not the same. Okay? Okay, now, so let's go back to this, the one that my mistake before. So now we say that this is a joint. Okay, let me remove this. Okay. So the mistake was good to show us something. So now, instead of defining this, now we define frame I. Okay. Now we want to define frame I minus 1. So frame I minus 1, if you build frame I minus 1, it will be based on frame I minus 2, correct? So now we say that we don't know, we only know here, we know the origin of this one, of frame I. But do we know the origin of frame I minus 1? We don't know. Yeah. Well, we can define it by defining using this convention. Okay. So if you want to define frame I minus 1, it will be based on frame I minus 2. Okay, the frame before it. So now this is frame I minus 2. So if this is frame this is Z of the frame I minus 2. This is the Z axis. Now, if this is the Z axis, I minus 2, and this is I minus 1, now we can define a common normal, the Xi minus 1. Okay, where is Xi minus 1? Again, it is the common normal and intersecting. So intersecting Zi minus 1 and Zi minus 2. So this is Zi minus 2 and this is Zi minus 1. It should be intersecting both axes. So now we can intersect here. Yeah, it's intersecting and it's also intersecting. Okay, so this is Xi minus 1. Intersecting both Zi minus 1, this is Zi minus 1, and Zi minus 2. So this is intersecting Zi minus 2. So now it is common normal. Well, is it normal? So well, because we orient the axis in some ways so that it will be normal. So this is normal, and this is also normal. Now we define your frame I minus 1. So this is frame I minus 1. Okay, where this is your Zi minus 1, this is your Xi minus 1, and your Yi minus 1 can be here. Okay. Any questions? Well, again, sir, is it okay to be here, the origin? Yes, it's okay. We can. Okay, that is also intersecting and perpendicular. Another axis also intersecting and perpendicular. Another axis also like that. But the thing is, only the location of the origin will change, and that location will be now defined with the parameters that we will be considering later. Okay. So in our case here, we define this as the origin of frame I minus 1, and we define this as the origin of frame I. Okay, what about the origin of frame I minus 2? Well, what do we need? We need the other axis here, frame I minus 3, Zi minus 3. Okay. If you want to define this, we need to define a frame before it. Okay. Sir, but sir, you told us that, we assume that frame I minus 2 is already defined. For example, our frame I minus 1 is already defined. In order for us to define frame I, You told us that frame I minus 1 is already defined. Yes, normally it is. For example, when you are doing a base frame, okay, with respect to the joint 1. Okay, let me change this one. This is a good, that's a good point. I want to remove everything so that you will know. For example, if we have one joint, okay, one joint, this is one link, okay, and it rotates about, this is your base frame, okay, okay, it rotates about that. So now, if this is just one joint, joint 1, that's joint 1, so this must be Z. If that is joint 1, this is Zi minus 1, so that Z0. So joint 1 rotates about Z0. Okay. So now, in this case, the base frame, it is up to you to define it. Okay. You can define your X0 to be here, Y0 to be here. That one can be arbitrary. You can also define where your origin is. Your origin can be here, your origin can be here, your origin can be down here. It's up to you to define. Excuse me. It doesn't matter. Okay, but the values of the parameters will change. Okay, I hope that is clear. Okay, so as you move, so now because your Z0 is defined, then you can define your Z1 and frame 1 because we already follow this convention. Okay, then as you move forward, okay, as you move forward another link there, you can also define your Z2 and so on. Okay. Okay, using those conventions, you will be able to define frame 1, frame 2, and frame 3. Okay. Okay, but we start with the base that is arbitrary. It's up to you to choose. Arbitrary in terms of the orientation, or in terms of how X0 and Y0 is oriented, as well as the location of the origin. Okay, and building on this frame 0, you can build frame 1, can build frame 2, and frame 3, and so on. Okay, so let's continue. This is one of the most fundamental information on robot control. That's why I spend a lot of time to explain this DH convention. So next, now the DH convention is the convention that will define how the frames are located and how they are oriented with respect to each other, with respect to frame I with respect to frame I minus 1, of frame I minus 1 with respect to frame I minus 2, or of frame I plus 2 with respect to frame I plus 1, of frame I plus n with respect to frame I plus n with respect to, what is that now? I plus n minus 1. Okay. Okay. So now, after you define your frames, now you will able to define now 4 parameters. Okay. Why you need 4 parameters? Again, you need 4 parameters because there are 4 basic transformations that will be done in order to define the relationship of the 2 frames. So in this case, let's concentrate on frame I. So we have defined frame I already before. So this is frame, okay, sorry. This is frame I. This is the origin of frame I. And this is frame I minus 1. Okay, so now we define the 4 parameters that we need in order to completely describe the transformation matrix between frame I minus 1 and frame I. So now, how do we do this? So there are 4 parameters as stated here: theta I, alpha I, di, and ai. Okay, so when you say angles, alpha and theta I, they are rotations. Okay, about, rotation about, rotation about, and then here di and ai, the letters. Okay, these letters, Hindu-Arabic letters, they are they define distances. Okay, the Greek letters define angles, the Hindu-Arabic letters define distances. Okay, so now how do we define this? So it says there theta I is, this is the rotation. I just say about because I made this one, I made this convention shorter so that you can easily imagine them. I'm the one who changed this description so that students can easily follow. So theta I, when you say about, it is a rotation. About zi minus 1. So where is zi minus 1? So we have defined this to be our zi minus 1. Let's concentrate on this one now. So we have two frames. Frame I minus 1 and frame I. So this is your zi. So now we need to define how is frame I with respect, what is the relationship with frame I with respect to frame I minus 1. So this is a joint I, yeah, and it rotates about zi minus 1. So when it rotates about zi minus 1, we say about zi minus 1. It rotates about zi minus 1. So this is your theta I. Okay. What about alpha I? It rotates about xi. Where is xi? Xi is this. It rotates about xi. Where is the positive? So this direction. This is the direction. That's theta I. What are the values? Later we'll see. But I'm just saying that this is the rotation that we are trying to define. This rotation about xi and rotation about the zi minus 1. Okay. Now, distance along zi minus 1. Distance along zi minus this one. This is distance along zi minus 1. And so the distance here, there is a distance along this axis where your di is defined. And then now, another distance along xi. So the distance along xi. This is your xi, where your ai is defined. Maybe you see the pattern now. Okay, so to define the four parameters, for the Denavit-DH parameters, theta I, alpha I, di, and ai, we're going to use two axes only, the zi minus 1 axis and the xi axis. Okay, so now how do we do this? So we say it is about zi minus 1. So let's consider theta I. Theta I about zi minus 1. So this is the one from xi minus 1 to xi. So where is xi minus 1? Xi minus 1 is oriented this way, from here to there. Okay, so that means that if this is parallel, of course we can transfer xi here because we're only considering rotation. So this is parallel to xi minus 1. So for us to easily see where is theta I, so this is xi minus 1. Now from here to there, rotates from here to there. So now from here to there, this is this theta I. Okay, you see that? This is the value of your theta I. About zi minus 1 from xi minus 1. This is xi minus 1 axis. Where xi minus 1? This is your xi minus 1 axis. And then this is your zi minus 1. Okay, then you sweep towards xi, from xi minus 1 to xi. So from xi minus 1 here, about zi minus 1, from here, from xi minus 1, sweeping towards xi. So that is your theta I. Any questions? Okay. Okay, let's pause for a bit so that you can imagine that. Next, alpha I. Alpha I is about xi. So again, where is your xi? This is your xi, about xi. So this rotation. Okay. Now, from zi minus 1 to zi. So where is your zi minus 1? This is your zi minus 1. To zi, where is your zi? This one. So we can make an angle, an axis that is, okay, it's not very clear here that this one is parallel to zi minus 1. We can transfer zi minus 1 so that we can easily see it. Okay, this is parallel to that. Okay, so now you can do with your right hand, by right hand rule, to say this is your xi, this is your xi, and then start from zi minus 1, you sweep toward zi. Okay, this is your xi, from zi minus 1, you see, about xi from zi minus 1. Okay, you start here with the zi minus 1, and this is your xi, and you sweep towards zi. So when you sweep towards zi, this is the sweeping now. This sweeping. Okay, so now this is your alpha I. Okay, any questions? Maybe you'll ask why I transferred the axis to here. Okay, again, I'm saying, just like I mentioned before, that the rotation, all the rotations can be rotations are independent of position. So that's why the axis can be transferred, the origins can be transferred, that the effect is the same. So in this case here, so that we can easily imagine what is the relationship, what is the rotation from zi minus 1 to zi. So we transfer this axis to here, to the origin, so that you can easily see how the angle is sweeping about xi from zi minus 1 to zi. Okay, so now those are the two angles. Let's do the distances. Let's just clear all drawings. Okay, so now let's do the distances now. So let's just draw zi again. That's the z. It's another z. So this is zi. Is it noisy? Is my sound from the cutting of the grasses? You can hear? No, I cannot hear. Yeah, there's a lot of noise here, the cutting of the grasses. Okay. Okay, so now this is your axis. So now let's consider distances. So along zi minus 1 from the origin of the I minus 1 frame. So our origin of I minus 1 frame, this we have chosen this to be your I minus 1 frame. And you have chosen this to be the origin of your ith frame. Okay, so that origin and this origin. Now along, so we are considering here along zi minus 1. So we are considering along this axis from the origin. So where is that origin? This origin to the intersection of zi minus 1 and xi. Where is the intersection of zi minus 1 and xi? This is your xi, right? This is your xi. Intersection of zi minus 1 to xi, this is the one. Okay, so along zi. Okay, if remember this is direction dependent. Okay, so that means that even the rotation before, I just didn't emphasize it, but these are rotation dependent. Okay, depending on the rotation, it can be positive or negative. If you're going sweeping in one direction, that's positive. If this is the positive x-axis, if you're sweeping in the other direction, and this is the positive x-axis or the positive axis, sweeping in the other direction, the sign will be negative. The same thing here, because you're moving along zi minus 1. So the positive zi minus 1 is in that direction. Okay. If you move from here to there, then that's positive. But if you move from here to there, then the sign is negative. So in this case here, along zi minus 1, from this origin, from here to the intersection to this one, from the origin of I minus 1 to intersection of zi minus 1 and xi, which is this one from here to there, that is along the positive direction. So in this case, your di is positive. Okay, so that is the first distance that we are considering. The second distance is along xi. Now this is xi. Along xi from the intersection of zi minus 1 and xi. This is the intersection. Zi minus 1 and xi. That's the orientation of intersection to the origin of frame I. Which is the origin of frame I? This one. Okay, and your xi positive is in that direction. So from here to there, that's along the positive direction. So this sign is positive, and this is your AI. We have completed all the conventions, all the 4 conventions. You have completed all the parameters, all the 4 parameters. Okay. So what's the use of all these parameters? Now, with all these 4 parameters, we can define the exact relationship of frame I with respect to frame I minus 1. How? Now, this is the 4 basic transformation matrices. Okay, there are 4 basic transformation of Z, transformation of Z by the distance D. Okay, distance, the Z-axis, along the Z-axis, a distance D, rotation about Z-axis of rotation theta, along, distance traveled along X of distance alpha, about of distance A, about X of rotation alpha. Let me just, okay. So this is translation along Z of distance D. So I've already mentioned before that when we are considering only distance transformation, we already consider this distance, and the rotation is identity. So here, we are only traveling, we are only translating in terms of distance, okay? And that distance is along Z-axis. So this is X, Y, Z. So the Z-axis is here. This is the transformation along Z-axis by a distance DI, which is the first transformation parameter. The first DH parameter. Next, rotation about Z-axis by theta. So now it's only a rotation, there's no position change. So here, position is 0. Okay, and then now you have the transformation, the rotation only. We know the rotation, basic rotation matrix of rotation about a Z-axis, right? We know this. So 0, 0, 1, 0, 0, 1. Rotates about Z-axis. Yes, cosine, cosine, minus sine, minus sine. And the angle is theta. Finish. We know that before already. Next. Along X-axis by an alpha by a distance A. Again, that is just translation. So this is identity. Translation of the distance along the X-axis. So this is the X-axis, AI. So nothing about Y and nothing about Z. Okay. Next. You rotate about x-axis by an alpha, by a value of alpha, by an angle of alpha. So again, the position is 0, rotation about x-axis. We know this. Rotation about x-axis is 1, 0, 0, 1, 0, 0. Because this is the x. Now, what are the terms here? Cosine, cosine, of course, then sine, sine. The angle is alpha, then negative and positive. We're done. We just compute this, multiply all these matrix, and now this is the basic transformation matrix for any frame I with respect to I minus 1. You don't need to memorize this. I will give you this during test. Okay. So once, I just want you to appreciate that these terms are done by, for sure, maybe if you don't somehow, if you don't have this matrix, you can derive it yourself. You can derive it by making those 4 basic transformation matrices. Translation about Z, translation along Z by D, rotation about Z by theta, translation along X by A, and rotation about X by alpha. Multiplying all those 4 matrices now will result into this matrix. Okay. Then now, what is the inverse? What is the inverse? Well, we know already that we can inverse this matrix by inverting the rotation and the position itself. How? How? So of course we know this, the inverse of this is the transpose. The inverse of this is transpose. So we just transpose this. We transpose that there. That's the case now. So we transpose this cosine sine theta, cos theta sine theta 0, cos theta sine theta 0. There, here, cos minus cos, this is now one, this one, and then that one. So we just transpose this, that is already the inverse. And then this one, how did you change? How did you see this? How did you take the inverse of this vector? With respect to I minus 1. Now with respect to I, sorry. Here is I minus 1. And the position of I minus 1. Which was that before? This one, I minus 1 to I, okay, then negative. This is the one. What is the physical meaning of that? Well, there are 2. Okay, let me explain this one because it will be easier if you can see the physical interpretation. If there are 2 frames, okay, let's just say frame 2, and then another frame 1. Well, you have this vector 1p2. Okay. Now, how do you express what is 1p2? This vector is expressed with respect to this point 2 is expressed with respect to frame 1, right? Now, what we want to do is, what is that position if we change the point of view now with respect to frame 2? That's the inverse of that vector p. Okay, so if we take the inverse of that vector p, now we take this point with respect to frame 2. Okay, you take this point with respect to frame 2. Okay, and also now you can see this. So previously the vector was in that direction, and now is in the opposite direction. that is the negative of that one. You take the negative of that vector. Now, but then because we want to express it with respect to frame 2 now, you multiply it with 1R2. Finish. That's why in your in the inverse of this is how you're going to express it. The negative, there's a negative sign multiplied by, here is not clear, multiplied by this rotation matrix, the inverse of this rotation matrix, or the transpose of that rotation multiplied by this vector. Okay. Okay, so much for that. Now we are ready to define what time do we finish here? We are ready to define any robot, no matter how the joints are located, we will be able to define what are the transformation matrices that we can relate, that we can describe the relationship between two joints. Okay, so between two joints, and now we can transform between three, from the base to the end effector. So we're going to start with, first example is the planar robot. Okay, remember the planar robot, we just did everything geometrically, but now we are going to define the parameters. We are going to define the DH parameter. We're going to assign frames here using the DH convention, and then we define the 4 DH parameters of alpha, theta, D, and A. So now you have distance D1, A1, alpha 1, and theta 1. So this is theta. Okay, so we define, how do we do this? We define the assignment of the frames with respect to the DH convention. So let's start with frame 0. Okay, so as we say, okay, this is Z0, it's not shown here. I mean, it's just perpendicular to the paper. And this is joint 1. Okay, so joint 1 rotates about Z0, and that is your theta 1. Oh, sorry, this is negative sign, negative theta 1. So positive sign is in that direction. Okay, so another, you always define the rotation, the axis of rotation. So normally, this is the axis of rotation of your joint 2. So this is a Z1 because that is joint 2. Okay, here joint 3. So this is your axis of rotation Z2. And when you take the end effector is that normally what people do is that the frame assignment of the n-1 frame will be the same frame assignment at the nth frame. Any questions? So now we have assigned all the Z0, Z1, Z2 up to Zn. In this case, this is Z3. Okay. And we know in this case here, your rotates about Z1, this is theta 2. Rotate about theta 2, Z2, that is theta 3. Okay. So now, because in this case, your thetas are the variables, so you just write theta 1, theta 2, theta 3. Okay. What are the values here? Well, maybe theta 1 is given as 30 degrees. I don't know, because there's nothing is stated here. If that is 30 degrees, that's fine. If this is 20, it's okay. We don't know. but it's not clear from the drawing. So because thetas are variables, so it's okay to define just like this: theta 1, theta 2, and theta 3. Okay. Next, we define alpha. So let's go back to what is your alpha? Let me bring up this so that you can see properly. I need this so that we can discuss properly. Okay. What is this? Why is that showing? Am I sharing my screen or no? Did I share my screen?
Yes, sir. It's
It's
gone now.
Huh? It's gone now.
Yes, sir.
Okay. This one. This is okay now. Okay.
Yes, sir.
Okay. Let's follow. Okay. So let me do it again. Your Z will be here. Okay. All the Z will be, okay, will be the axis of rotation. Then we say the last one is just parallel to this one. Okay. So now this is your Z0, Z1, Z2, and Z3. Okay. So XI is common normal and intersecting to both ZI and ZI minus 1. So where is your ZI? Okay. Now we want to, in this case here, your frame 0 is defined already. Okay. We define your Z0 here. This is your origin, and your Y0 is there, and your X0 is there. Okay. It can be arbitrary. Okay. Our X0 can be somewhere else. X0 can be there, and Y0 can be somewhere else. Oh, no, it cannot be because this is Z0. It could be here, or Y0 could be there. So anyway, as long as they're perpendicular, we can assign, they are mutually perpendicular, we can assign those axes. But in this case here, we assign our X0 to be there and Y0 to be here. Okay. Then the rest will build on that base frame. So now, so we say that Xi, okay, that means X1. We're looking for X1, intersecting both Z1 and Z0. So this is Z0 and this is Z1. So we intersect. It will intersect. Okay. This can be X1 because it intersects. This could be also X1 because they intersect. Are they perpendicular? Yes. Why? Because X1 is perpendicular to the plane of the paper, and Z0 and Z1, I mean, X1 is on the plane, parallel to the plane of the paper, and X0 and X1 are perpendicular to the plane of the paper. That is perpendicular, that's perpendicular. This is perpendicular, that's perpendicular. So which X1 you want to use? This is the origin. Yeah. Okay, of course, this is the origin now. And so we use X1 to be later on we know that x1 has to go through the origin of frame 0. Okay, so now of all the possible x's, this is one possible x, another possible x, is this another possible x, that's another possible x, that's another possible x. Okay, you choose this x that passes through the origin because we have already defined our frame 0. Okay, so this passes through the origin, and so now this is your x. So let's clear that one. Your z0, your z1. Where is your x1? Well, we already know your x0 is here. This is the origin. Y0. Okay, so we know that your x has to be both perpendicular and intersecting to z0 and z1. So we choose this to be our x1 because it is intersecting z1 and z0 and also perpendicular. Okay, and also it's not stated in there, also passing through the origin of frame 0. Okay, well, of course we can say that, well, we can choose to be like this, but then the parameters will change. This one is the most convenient for us. Okay, any questions? Again, I want to emphasize, you can choose here if you want your origin to be here, if you want the origin of frame 0 to be here, that's also okay. Then you have to transfer y0 to be here, y0 to be here if this is your origin, x0 to be here. Well, yeah, maybe that is not that is not the most accurate way of saying. Well, you can even say that I want to choose my frame 0 to be here, that's fine. But I want to choose this as my frame 1. That's also okay. So that means that this is your frame 1, that's your frame 0, and things will change in terms of the parameters. But the most convenient one is, of course, your frame 0 will be here. I mean, your frame 1 will be here. Any questions? We still satisfy the DH convention. Okay, so next, now let's just we'll take the parameters in the next session. But for now, let's just do another axis here. So if this is your axis Z1, I mean Z2, now where is your X2? Your X2 also is normal and intersecting Z1 and Z2. Okay, so again, you can have this axis X2 intersecting a normal, this one X2 also intersecting a normal. You can also use another here, okay, also like that, X2, because axis goes through, they don't end, you know. Axis, this is one whole line, this is one whole line, oh, sorry. This is one whole line of your Z2. This is still Z2. And this is also Z1. Okay, although in that direction, it's negative direction, and this is negative direction. The positive here is this direction. Positive here is this direction. Okay, but still, you know, you can have X2 there, and still it intersects, and they are perpendicular. Okay, that's possible. Again, the most convenient one is that it will pass through this physical joint. Okay, so we choose X2 to be here. Okay, so this is your x2 and that is your x1. Any questions? I'll stop here in terms of how we define your frame 0, your frame 1, and now your frame 2. Again, once you define where is your x2 and z2, that's it. You don't, the y2 only completes the right-hand coordinate system. It's not necessary for you to show. Okay, but once you define your x2 and your x2 and your y2 and z2, that defines your origin already. This is the origin of frame 2. The same thing. This is your z1 and that is your x1. So this is the origin of frame 1. So frame 1 is there. So now in this case here, we define frame 0 to be here, frame 1 to be here, and frame 2 to be there. Any questions? Okay. In the next, in the lab session, we're not ready for the next lab. So I won't give any lab exercise next meeting because I'm preparing. Once we finish this, then we'll have 2 labs. One is the computation and the other one is your MATLAB program. Manual computation and the other one will be MATLAB. So we will rest this week, but then next week there will be two exercises. One is the computation and the other one is the MATLAB program. Some more questions? It's already 1 o'clock and I have to go. Let me stop sharing. No questions? Did you understand? Please somehow go through the slides again. I will upload the video and of course cut that call, and then I will and then go through the discussion again for you to understand. If you have any questions, please ask me in the WhatsApp group or in the email. Okay, or we can even discuss if you want to do a consultation. We have consultation hours that you can schedule with me if you want to discuss some questions on the topic today. Okay. Okay. Yeah, having said that, I have to go, and let's call it a day. Thank you very much. Bye, everyone. Okay, wait, let me have the attendance before. Wait, cancel. I want to show everyone's faces, view, so that it will be my attendance. Okay, where are you? The faces. Okay, my attendance. Smile. Okay. There, did you see the screen clip? So now, Chicago and Leslie, you're not there. Okay. Bye, Farhan. Bye, everyone. See you next meeting.